Good morning. Today, as I mentioned last time, we're going to study a boundary value problem involving, at some point, the Cauchy-Euler equation, which we studied in the previous lecture. And this is actually the first, well, I suppose the more involved problem that we're going to solve, dealing with other coordinates than Cartesian coordinates. So in particular, we're going to deal with cylindrical coordinates. Although in this case, because the object of study is a plate, it's two-dimensional. Technically, we can call these polar coordinates because the z coordinate, right? So if you remember, the in cylindrical coordinates, you have essentially polar coordinates for two axes, and then the Cartesian coordinates for the remaining one, for the z-axis. So there's no z-axis here because the object is of two dimensions. So it's basically a plate of negligible thickness, if you want. So before I continue, I really want to strongly emphasize my previous advice, which I mentioned several times during this class. This topic, it's really not the one that you want to rush. So take your sweet time, especially since now you have this option to pause the video at any time you want and maybe rewind it. And don't move on to the next step until you really understand every single step in the process, starting, of course, with the formulation of the problem. So before we do any math, let's make sure we understand the formulation of the problem. So we have a heat equation problem, namely a steady-state temperature, and the object leads naturally to a different set of coordinates than Cartesian coordinates because of its shape. So we have an object basically in the shape of a plate situated between two circles, but in a quarter of a circle basically. So only the dashed portion is the actual object. So basically you have the inner circle of radius 1, the outer circle of radius 4, and then the plate is right here in between these straight edges. So how do we describe, and again, let's assume that the heat flows along the polar coordinates basically, or cylindrical coordinates if you want, and with respect to the time t. So u, the temperature of any point on the plate, is identified by the cylindrical coordinates rho, phi, and t, and not on z, right? I mean, again, there's no z coordinate. T is the time as usual. To use the notation in the book, rho is the radius. Okay, so for a typical point, the distance between the origin and the point is rho, and then the angle in the counterclockwise orientation is phi. And then the time t. So the heat equation in this case, generally speaking, will be u partial t equals some constant a squared, and then the Laplacian in cylindrical coordinates, the portion only that depends on rho and phi, which is rho square, which is u differentiated with respect to rho twice, plus 1 over rho u partial rho, plus 1 over rho squared u partial phi twice. So the partial derivative with respect to phi twice. Again, you can pause for a moment and look at the Laplacian in cylindrical coordinates. So look for the Laplacian in cylindrical coordinates. And in that Laplacian, replace partial z with 0, because again, our object doesn't depend on the z coordinate. So you're left only with this quantity. Okay. So we say that we want to study the steady state temperature. So basically, steady state temperature means that if we assume that after some initial conditions and boundary conditions, the temperature doesn't change with respect to time anymore. Remember, that means we assume that at some point partial t will be 0. What's left in the PDE will give us the final temperature distribution. So the steady state equation, or the steady state PDE, the PDE that gives you the steady state temperature, would be just the Laplacian equal to 0. So this is essentially the problem that we want to solve with the appropriate boundary conditions. And remember, in Cartesian coordinates, some of these problems were really trivial because in the case of a one-dimensional rod, the Laplacian was simply uxx, right? So u partial x twice, and it was just basically a calculus 2 problem of integrating twice. Now, we're not in Kansas anymore, so we have to deal with a much trickier problem, or longer at least, if not trickier. I should mention here that notice, because rho is never 0, right? So I mean, we're going to establish the boundaries immediately, the domain for the variables, but we can see that the radius is going to be between 1 and 4. So we can actually multiply this equation by rho squared just to make it a little bit nicer to handle, and then we're going to deal with the appropriate boundary conditions. So once I multiply by rho squared and simplify, the PDE becomes rho squared u partial rho twice plus rho u partial rho, and then plus u partial phi twice equals 0. And now, very carefully and slowly, let's figure out the boundary conditions. Well, first of all, the domains for phi and rho, and then the boundary conditions. So as I mentioned already, the radius is between 1 and 4. Okay, so as we describe the object with a rays like this from the origin, clearly the domain is 1 and 4 for the radius. Then in the counterclockwise motion, starting with 0 from the positive semi-axis, the domain of phi, take a moment to actually figure it out, is going to be 0 and pi over 2. 0 and 90 degrees. So these are the intervals of rho and phi. So some problems are written in words, right, when they describe the process. So let's see how we get from the words to the condition. So it says that the horizontal and vertical straight edge, or straight sides, that is this and this, are kept at 0 temperature. So from a physical perspective, for the problem to be well posed, obviously I need to know what happens on the boundary of the object. And the problem says that this edge and this edge are kept at temperature 0 at all time. It's very useful to pause the video for a moment and try to actually write the condition yourself. Again, I can't tell you if you do that because you're on your own, but trust me, it's very useful if you attempt. Just pause the video, try to write the boundary conditions related to this description of the problem, and then check. Okay, so assume you just did that. Let's see. The horizontal straight edge corresponds to phi equals 0. Okay, so the time variable doesn't matter anymore because we deal with a steady state temperature. So at this point, u is assumed to depend on rho and phi. So phi equals 0 describes this edge. So that means the boundary condition is going to be u of rho 0 equals 0. And the same thing for this edge. This edge corresponds to the angle pi over 2, radius between 1 and 4. So u of rho pi over 2 is also 0. So these are homogeneous boundary conditions of Dirichlet type. That means you have prescribed 0 temperature at that edge on the boundary. So again, rho varies. 0 is phi equals 0 describes this edge. Phi equals pi over 2 describes this edge. What else does the problem say? The inner round edge, this one here, is kept at 0 as well. So that's also a homogeneous condition. Now, how do I describe this one? Well, here the radius is constant. So rho is 1, but phi varies. Okay, so I'm going to write this as u of 1 phi equals 0. And then finally, the non-homogeneous condition, which remember it's dealt with at the end in the process. It says that the outer round edge temperature is phi squared. So for the outer edge, the round one, the radius is 4. And we set this equal to phi squared. All right, so that is the formulation of the problem. Let's now do the separation of variables very carefully, and let's identify the Sturm-Liouville problem, which is to be solved first. It's very important to understand that the process is really the same, okay? But now we have a different context, different variables, different meaning of the variables, but the main idea is still the same. We assume that our dependent variable has a product form, a function in rho and a function in phi. And again, let's try to use suggestive notations because rho denotes the radius. Let's call the function in rho big R. There's no requirement to do that, but it makes sense. And the function that depends on little phi, let's call it big phi. And then let's plug in this product form into the PDE. Very carefully, right? So we have rho squared, partial rho twice is going to be R double prime times phi. Remember, at this point, we don't have to write the of rho or of phi. I mean, we already understand that big R is a function of rho, big phi is a function of little phi. And we can use the prime notation because these are single variable functions. So the middle guy here is going to be rho R prime times phi, and then plus partial phi twice, that's going to be R phi double prime equals 0. Next thing to do, plug in the product form into all the conditions, the homogeneous condition that is. Remember, the non-homogeneous one is dealt with at the end after superposition principle, but the homogeneous ones become big R of rho phi of 0 equals big R of rho phi of pi over 2 equals 0. And we have another homogeneous condition, big R of 1 big phi of little phi equals 0. And remember, we're looking for non-trivial solutions. Let's see, it was, I think, a little bit out of range. So let's do this, the actual separation. And remember, if we presume already which of the two will be the Sturm-Liouville problem, make sure, as a rule of thumb, to keep that Sturm-Liouville problem as clean as possible. So any possible extraneous constant, which is not the case here, but in general, just leave it to the other problem and leave the Sturm-Liouville problem as simple as possible, because you may recognize it as one that you solved before. And you should already anticipate that phi will be the Sturm-Liouville problem. Notice that this condition here in the middle on this row will lead to phi of 0 equals phi of pi over 2 equals 0. So that will be the homogeneous boundary value problem. And like I said, let's do the separation. So what I can do over here, I can pull out phi, and let's move the last term to the right-hand side. This step, remember, it's not always clear cut because it depends on the algebra manipulation. So big phi times rho squared R double prime plus rho R prime equals minus R phi double prime. And divide by minus R, and what else? Divide by phi to move it from the right to the right-hand side. So in a separated form, the equation looks like rho squared R double prime plus rho R prime over minus R equals phi double prime over phi equals minus lambda, the separation constant that you introduce at this point. Pause for a moment and realize that this is what you have met before. It will lead to a Sturm-Liouville problem, which is already solved beforehand. We don't have to go through the whole process to find the eigenvalues and functions. We just adapt it to our notation here. So let's write them down here separately. I'm going to write them down on the second page as well. So the eigenvalue problem, or the Sturm-Liouville problem, is phi double prime plus lambda phi equals 0. And again, from this portion of the boundary conditions, we have phi of 0 equals phi of pi over 2 equals 0. So this is the problem to solve first. The other problem, which is to be solved for every eigenvalue and eigenfunction, is the problem in R. So if we multiply minus R with minus lambda and move it to the left, let's actually do it right here. So rho squared R double prime plus rho R prime equals lambda R. And if we move it to the left side, becomes rho squared R double prime rho R prime minus lambda R equals 0. And this one also has a homogeneous condition that we can deal with before superposition principle because of this condition. So R of 1 equals 0. Again, this extra boundary condition homogeneous is not always, doesn't always happen, right? I mean, you need to have basically, of course, homogeneous conditions for the Sturm-Liouville problem, but some problems may also have extra homogeneous conditions, and you always deal with them before you deal with the non-homogeneous condition. It might be worthwhile to go over the guidelines of separation of variables, and again to read that part which says the separation of variable method essentially works when you have all conditions homogeneous except one. So you can afford yourself basically one non-homogeneous condition. Okay, so let's actually split this lecture in several parts. We're going to continue to solve the problem on the second part.